Today in this session we are going to talk about adjoint of a matrix and the inverse of matrix with the help of adjoint of a matrix. See how the adjoint of a matrix is defined. See, if we are having a square matrix A, then the transpose of its cofactor matrix is known as the adjoint of the matrix. See, if I have a square matrix A, then the adjoint is defined as the transpose of the matrix Aij, where this Aij is the cofactor of the element Aij. Suppose I have a matrix A, 2 by 2 matrix, a square matrix which has elements A, B, C. The cofactor of this, we have studied about the cofactors. To find the cofactor, we multiply it by the minor, we delete ith row and jth column, and the determinant obtained so is known as minor. And if this minor is multiplied by minus 1 raised to I plus j, that is for this it will be positive. For this 2 plus 1, odd power of minus 1, it is negative. Again 2 plus 1 is negative and positive. So the cofactor of this will simply be d. The cofactor of this b will simply be minus c. The cofactor of c, that will be simply b, and the cofactor of d, this will be eliminated for this a. Now the adjoint is transpose of A, transpose of the cofactor matrix, transpose of cofactor matrix. So we write the cofactor matrix. The corresponding cofactors will be written d minus c minus b a. Now we take the transpose. Transpose is not about rotating but about interchanging the rows and columns. So now the first row becomes the first column, that is d minus c, and the second row becomes the second column. This is how we find the adjoint of a matrix. Suppose I have given a 3 by 3 matrix. That how I will find the adjoint? Simply I'll find all the 9 cofactors of all the elements and I'll take the transpose of the cofactor matrix. That's how we find the adjoint of a matrix. Now let's talk about a short inverse of a matrix. A inverse is equal to 1 upon determinant A times of adjoint A. The inverse of A is given as adjoint A divided by determinant of A, provided that determinant A is not equal to 0. If determinant A is not equal to 0, then only the matrix is invertible. We'll talk about it on a later stage. Right now we are trying to find the inverse. How? Now here for this matrix, the determinant is AD minus BC. AD minus BC. Now so A inverse is equal to 1 upon AD minus BC and the adjoint A divided by determinant A. So this is determinant A, 1 upon determinant A times of adjoint A. See, if you have a 2 by 2 matrix, then it is very simple to find its inverse. We have used elementary row transformations and column transformation in the previous chapter. Now it's very easy and we will develop a short trick to use to find the inverse of a 2 by 2 matrix. Let's see how. See, this is a standard 2 by 2 matrix, that is A11, A12, A21, A22. Now we'll find, to find the adjoint, what we need is, we need the cofactor. Now after cofactor, finding the cofactor, what we'll do, we'll find the cofactor matrix and transpose it. The transpose of the cofactor matrix is adjoint. The transpose of cofactor matrix is the adjoint of matrix A. Okay, so let's find the cofactors. The cofactor of this will delete this ith row and jth column. So this and this will be deleted. So this is the cofactor. For this, cofactor will be 1 plus 2 minus 1 raised to 3 is negative. So this is for this negative of minus A21. For this 2 plus 1 is negative. So odd power of minus 1 is negative. So this row and this column will be deleted. A12. For this row column and this row will be deleted. So A11 positive. This is the cofactor matrix. So adjoint A is transpose of cofactor matrix. The cofactor matrix is simply A22 minus A21, then A12, A1 minus A12, A11. Now transpose, on taking transpose, this row will become the column and second row minus A12, A11 will become the second row will become the second column. Now you can observe, this was the standard matrix A 1 1 1 2 1 1 1 2 2 1 2 2, and this is the adjoint A. So A inverse is nothing but 1 upon by definition we will talk about it. A inverse is 1 upon determinant A of times of adjoint A. This is this is the proof. We'll talk about it. Well, so A inverse is 1 upon determinant A times of adjoint A, and adjoint A is here. You can see from the original 2 by 2 matrix, if we interchange the elements of leading diagonal, just interchange it. A11 and A22, these are interchanged. Just interchange the elements of leading diagonal and change the sign. Do not interchange them, just change the sign of non-leading diagonal elements. You will find the adjoint, and if you divide the adjoint by determinant A, you are going to get the inverse of a matrix. So we have done in the previous chapter, we have used elementary dot transformation. It took a lot of time. Here you can just by observation you can find the inverse. What you are to do is 1 upon determinant A times of 1 upon determinant A times of, just interchange this and sign change. Interchange the leading diagonal element and change the sign of the non-leading diagonal element. That is how we find the inverse of a 2 by 2 matrix. The process is very simple. If we are to show the process, we'll find the adjoint A. With the help of cofactors, we'll find the transpose of cofactor matrix, and then we'll divide it by the determinant of A. That is how we do. Now we can practice those questions which we have done in previous chapter, that is in the chapter matrix. For 2 by 2 matrix, what we do, we interchange these elements, just interchange the elements of leading diagonal, and we change the sign of non-leading diagonal elements, and the inverse is given as 1 upon determinant. So first of all we find the determinant of A, that is here determinant of A is 3 plus 2, minus of minus 2 is plus 2, 3 plus 2 is 5. So A inverse is 1 upon determinant A. Determinant A is 5 here, and we interchange this. For adjoint A, what we do? Interchange it. So 3 and 1 will be interchanged. 3, 1. And here we will change the sign. This will be plus 1 and this will be minus 2. This is the answer. So you can check the answers quickly for all your questions, and your teacher do like this. Simply here the A inverse is 1 upon determinant A. 7 2 is 14 minus 5 3 is 15. 14 minus 15 is minus 1 times of. What you will do? Interchange this. So this is 7 to change the sign of these two, minus 5 minus 3. Now we have to divide it by minus 1. So this will become, all the sign will be changed, that minus 7 3 plus 5 minus 2 is the inverse of this matrix. Here in the very first step you can see the determinant of A is equal to 2 into 2 minus 4 into 1, that is 4 minus 4 is equal to 0. So A inverse does not exist, because to find A inverse we have to divide by determinant A, and division by 0 is not defined. So for the matrix whose determinant is 0 is known as singular matrix, and singular matrix cannot be inverted. Well, here in this one, simply A inverse, you can see 2 2 is 4, 2 into 2 minus 1 into minus 3, that is 4 minus 3. 4 minus 3 is 1. So 1 upon 1 times of, just we are to interchange these. So 2 2, and we have to change the sign of 1 3, and we have to divide it 1, but that is nothing to do. This is the inverse of this matrix. That's how quickly we can find the inverse of a 2 by 2 matrix. After practicing the inverse of a 2 by 2 matrix with the help of adjoint, we must take example 25. Example 25 on page 130 in Ncert textbook. We are given A as 2 3 1 minus 4, and B is a matrix of order 2 by 2, and we are to verify the reversal law of inverse. AB inverse is equal to B inverse into A inverse. It can be generalized as ABC whole inverse is equal to C inverse into B inverse into A inverse. Inverse is in reverse order, reversal law. So to find the left hand side, first of all we need to find AB. So we have A, this is 2 3 1 minus 4 into B, that is 1 minus 2 minus 1 3. Now to find the product, this row will be multiplied by the corresponding elements and will be added. 2 into 1 plus 3 into minus 1. 2 into 1 plus 3 into minus 1. Now this will be multiplied by this, will return here 2 into minus 2. 2 into minus 2 plus 3 into 3. 3 into 3. Now second row will multiply by first column. So 1 into 1, 1 into 1 plus minus 4 into minus 1. Minus 4 into minus 1. Now this will be multiplied by this 1 into minus 2. 1 into minus 2 plus minus 4 into 3. Minus 4 into 3. So simply AB is equal to, this is 2 minus 3 is minus 1. This is minus 4 plus 9 is 5. This is 1 plus 4 is 5. This is minus 2 minus 2 minus 12 is minus 14. Minus 2 minus 12, that is minus 14. Now we have to find the inverse, and inverse is simply 1 upon determinant of that matrix times of adjoint A. So first of all we will find the determinant of AB. Determinant of AB is nothing, this into this minus this into this, that is minus 1 into minus 14 minus 5 into 5. This is plus 14 minus 25, that is minus 11. Since the determinant of AB is not equal to 0, so AB, the matrix AB, we can name it as C. So this matrix AB is invertible. To find the inverse of any matrix, first of all we must ensure that it is invertible or not. Now AB inverse. How we find the inverse of a 2 by 2 matrix? 1 upon determinant of AB into adjoint of AB. Find it. How we find that? 1 upon determinant of AB, that is 1 upon minus 11. C. The adjoint of any matrix is obtained by interchanging the elements of its leading diagonal and by changing the sign of non-leading diagonal element. We will interchange these two elements. These two elements will not change their place, only the sign will be changed. Well, so here is AB. What we will do is, we will simply interchange these two elements, that is minus 14 minus 1, and we will change the sign of these two. This will minus 5 and this will also be minus 5. This is equation 1. Our left hand side is ready, AB inverse. Now for right hand side, what we need? We need A inverse. So here, now for right hand side, now for RHS, here determinant of A. Determinant of A you can find minus 8 minus 3. Minus 8 minus 3 is equal to minus 11. So A inverse exists. Now A inverse is equal to 1 upon determinant A times of adjoint A. 1 upon minus 11 times of adjoint A. How you will find adjoint? Simply interchange these two. For it, interchange these two, minus 4 2 and change the sign of these two. So minus 1 minus 3. Also now determinant of B, here this is B, so determinant of B is 3 minus 2, that is plus 1, which is not equal to 0, so B is invertible. Now B inverse. B inverse is 1 upon determinant B times of adjoint of B. So 1 upon minus 1, sorry, 1 upon 1. 1 upon 1, determinant B is 1 times of adjoint of B. Hello. How will you find the adjoint? Simply interchange this 3 1, 3 1, and we'll change the sign 1 2. Hence RHS is equal to B inverse into A inverse. We have to prove that AB inverse is equal to B inverse into A inverse. Now B inverse, A inverse. Where is B inverse? This is 1 upon 1, that is 1 only. So this is 3 2 1 1 into A inverse. A inverse is 1 upon minus 11 times of minus 4 minus 3 minus 1 2. So this 1 minus 1 upon 11 is here. So we multiply these two matrices. We can write it like this, minus 1 upon 11 times of this. Now see the product. 3 into minus 4, minus 12 minus 2. Minus 12 minus 2 is minus 40. This will be multiplied by this minus 9 plus 4. Minus 9 plus 4 will give me minus 5. Again, this will be multiplied by this minus 4 minus 1 is minus 5. This will be multiplied by this minus 3 plus 2. Minus 3 minus 2. Minus 3 minus 2 will give me minus 5. Sorry. Minus 3 plus 2 is minus 1. So this will give me minus 1. So this is equation number 2 from 1 and 2. See, the right hand side of equation 1 and right hand side of equation 2 are same. So we can see B inverse A inverse is equal to AB inverse. So AB inverse is equal to B inverse A inverse. These two are equal. Minus 14 minus 5 minus 5 minus 1. So this is how we find the inverse of a 2 by 2 matrix quickly with the help of adjoint of A. Now we'll talk about other questions. Right. Now let's talk about this property. See this property. A times of adjoint A is equal to determinant A times of I. That is same as adjoint A into A. See, this is our A matrix and this is adjoint A. Adjoint A is the cofactor of A11 is corresponding to A11 is A11. A12 is A12 and we will transpose it. Transpose of cofactor matrix I have written here. 1 1 1 2 1 3 1 1 1 2 1 3 we have transposed. The corresponding cofactors are here written here and the corresponding cofactor of this row is written here. So this is A and this is adjoint A. When we multiply, the multiplication of matrix is row by column. The row will be multiplied by column. Just run and jump. So A11 A11 into A11 A12 into A12 plus A13 into A13. Now the first will go here, A11 into A21, A12 into A22, A13 into A23. Again the first 1 3 position, this is 1 3 position. For 1 3 position, first row with third column. So A11 31 1 2 3 2 plus A13 3 3. Suppose I need this position, this is the product, the which element? Third row, second column, 3 2. So third row will be taken from first and second column will be taken from this. So A31 A21 A31 A21 A32 A22 A32 A22 A33 A23. Well, in the previous session we have discussed two properties. One, if we choose a particular row and multiply its element with the corresponding cofactors and find the sum, then it is equal to the value of the determinant. But if we choose a particular row and multiply it by the cofactors of any other row, then the product is always 0. So here you can see we have chosen the elements of first row and multiplied it by the cofactors of same row. So this will become determinant of E. In the same way 2 1 2 1 2 2 2 2 2 3 2 3, it is multiplied by elements of second row are multiplied by the cofactors of second row. Here also element of third row are multiplied by cofactors of third row. So this will give us determinant A. But all these, here what happened? We have taken 1 1 1 2 1 3 1 1 1 2 1 3. The elements we have taken from first row, but the cofactors are of second. 2 1 2 2 2 3 2 1 2 2 2 3. So if we multiply the elements of a particular row with the corresponding cofactors of any other row, then the product is always 0. The sum of this product is. So this is 0. This is 0 as well. This is 0. This is 0. This is 0. This 0. This is A and this will give us 0. So 0 0 0 0. This is a matrix. So we can take determinant A common from each and every element. So dividing all the elements by determinant A, we get 1 0 0 0 1 0 0 0 1 and that is I. Determinant A times of I. A into adjoint A. A into adjoint A. A into adjoint A is always equal to determinant A times of I. This is the important property which we are going to discuss today. First of all, we will discuss two multiple choice questions so that the concept what we have studied must be clear. Well, let's talk about the process of finding the inverse. See, we have A into adjoint A is equal to determinant A times of I, right? Just now we have proved A into adjoint A is equal to determinant A times of I. Now, if we pre-multiply both the sides by A inverse, then this is A inverse into A, adjoint A is equal to A, determinant A is a constant, so determinant A times of A inverse I. If I multiply something by I, the result is itself, anything into I is equal to itself. Well, here A into A inverse, obviously A into A inverse is a unit matrix, that is identity matrix, so A into A inverse is I into adjoint A is equal to A inverse into I is A. Now you can see if any matrix is multiplied by I, any matrix multiplied by I is the matrix itself, so this will be equal to adjoint A. So adjoint A is equal to determinant A times of A inverse. We need to find A inverse. So the value of A inverse, this is constant, so we will divide it, dividing both the sides by determinant A, provided that determinant A should not be 0. That is the most important thing. So whenever we will try to find the inverse of a matrix, first of all we will find the determinant of A to decide whether the inverse of the matrix can be found or not. If the determinant of a matrix is 0, then it is said to be singular, and if the determinant of a matrix is non-zero, then it is said to be non-singular, and the non-singular matrices are invertible. Well, so here on dividing both the sides by determinant A, we find A inverse is equal to 1 upon determinant A times of 1 upon determinant A times of adjoint A. A inverse is 1 upon determinant A into adjoint A. And for a 2 by 2 matrix, it is very simple. What we do is just interchange the elements of leading diagonal, and we change the sign of elements of non-leading diagonal elements. That's how we do. Now let's talk about the two MCQs given in the exercise. The last two questions. The last one is, if A is a matrix, then what will be the value of determinant of A inverse? See, we have A into A inverse is equal to I. Determinant of I is always 1. Whatever order of the matrix I is, the value of its determinant is 1. One more important thing, determinant of A into B is equal to determinant of A into determinant of B. It can be generalized, determinant of A into B into C is equal to determinant of A into determinant of B into determinant of C likewise. So if this is a matrix equation, if I take the determinant of both sides, A inverse is equal to determinant of I, obviously this will be determinant of A into determinant of A inverse is equal to determinant of I, which comes out to be 1, and determinant of A inverse is equal to A into B is equal to determinant of A into determinant of B. So determinant of first into determinant of second. Now I need the determinant of A inverse. Determinant of A inverse. So I will divide both the sides by this. So I can write determinant of A inverse is always equal to 1 upon determinant of A. This is how. This is the question. This is the 18th MCQ in our textbook, NCERT textbook, page number 132. If A is an invertible matrix means determinant A is not equal to 0, so we can divide both the sides of an equation by determinant A. Of order 2, whatever the order is, this holds true always. Determinant of A inverse is equal to 1 upon determinant of A. 1 upon determinant of A. Then determinant of A inverse is equal to 1 upon determinant of A. Well, there is also given last MCQ. If A is an invertible matrix of order 2, then let A be a non-singular square matrix of order 3 by 3, then determinant of adjoint A. See, we need the determinant of adjoint A. See, we have a formula. We can remember the formula, and it must be there on our mind, determinant of A, adjoint A is equal to determinant A raised to n minus 1, where n is the order of the matrix. So here the order of the matrix is 3 by 3. So adjoint A simply will be determinant A raised to 3 minus 1 is equal to determinant A whole square. This is the formula. Now where this formula has come from? Exactly from here only. We have A into adjoint A is equal to determinant A times of I. Okay. Taking determinant of both the sides. Well, so this will give me determinant of A into determinant of adjoint A is equal to C. A in a matrix, this is a matrix, the determinant of this matrix, K times of A, the matrix of K times of A is equal to K raised to n times of matrix A, because K will be taken, this is actually, if a 3 by 3 matrix is, then it is determinant A 0 0 0, determinant A 0 0 0, determinant A. If I take determinant A common, then it will be taken once from here, determinant A again from this, then determinant A cube, that is the equal to its order. So this will give me determinant A raised to n times of determinant matrix, determinant of I. Now you can see the determinant of I is 1. So determinant of A into adjoint A is equal to, so determinant of A raised to n, because determinant of I is always equal to 1. So this is something into 1 is A raised to n. Dividing both the sides by determinant A, determinant A raised to n upon determinant A, that is determinant A raised to 1. So 1 power will be subtracted. This will give us the formula adjoint of A is equal to determinant of A raised to n minus 1. This is the most important thing, which on this, in most of the competitive exam, on this formula questions are being asked. The value of adjoint A, the determinant of adjoint A is equal to n minus 1 power of determinant A. There is another formula, adjoint of adjoint A. The determinant of adjoint A is equal to determinant of A raised to n minus 1 square. Sometimes in some competitive exams this formula is also useful. Now we'll proceed to for this MCQ, particularly if we talk about the 17th MCQ, the value of adjoint A, when the order of A is 3, then value of adjoint A is equal to determinant A raised to n minus 1. So determinant A raised to 3 minus 1, that is determinant A square. So B is the correct option. Now we take some other questions. Well, we have taken a question number 10 from exercise 4.5. Here we are to find the inverse of the matrix. See, if exists. Whenever we try to find the inverse of a matrix, first of all we check whether the matrix is singular or non-singular. For a matrix to be invertible, it must be non-singular, that is, its determinant must be non-zero. If the determinant is non-zero, then it is non-singular. If the determinant of A is not equal to 0, then it is said as non-singular matrix. Well, if I have a determinant C 2, 3, 4, 5, then if I have a matrix, then here the determinant of this matrix is 5 2s are 10 minus 4 3s are 12, that is minus 2 is not equal to 0. So A is a non-singular matrix. So A is invertible. Simply because we have A inverse is 1 upon determinant A times of adjoint A. So to divide something by determinant of A, determinant A should be non-zero. So here we have a condition that the determinant should be non-zero. So first of all, what we do is, first of all, in any question, let us name it with matrix A. Now, first of all, to find the inverse, we have the formula here. We have A inverse is equal to 1 upon determinant A times of adjoint A. So first of all, we'll ensure that the matrix is invertible or not. So we will find the determinant of A. Now, the determinant of A here, the determinant of A, expanding it along first row. So 1 multiplied by 2 fours are 8 minus 2 into minus 3 is plus 6, 8 minus 6. Now the cofactor of this element is negative, so minus of minus 1 times of, I will eliminate this row and column. So 0 into 4 is 0, minus of minus 9. Minus of minus 9 is plus 9. Well, plus. Now 2 will be multiplied by its corresponding cofactor, that is 0 minus 6. 0 minus 6. This will give us 2 plus 9 minus 12. So this is simple. 2 plus 9 is 11 minus 12 is equal to minus 1, which is not equal to 0. So A is invertible. A is invertible. Mind it, whenever we are to find A inverse, first of all, we must try to find the determinant of A. If the determinant of A is non-zero, then only we will proceed. Otherwise, we will say if determinant A is 0, then we will say it is non-invertible. Now, we need to find the adjoint A. What is adjoint A? The transpose of cofactor matrix. Now, let's see how the cofactors are found. See, 1 1 1 2 1 3. A11, A12, A13, A21, A22, A23, A31, A32, A33. Capital A, Ij denotes the cofactor of the element small a, Ij. See here, I'll write plus, 1 plus 1 is plus, here I'll write minus, and I'll put a bracket, then plus 2 plus 2 is even power of minus 1, this is plus, this is minus, again here plus, and likewise 3 plus 2 minus, 3 plus 3 6, that is even, this is negative. Now how we do this? Now the cofactor of this is simply this, 2 4s are 8 minus 6, 8 minus 6, and that will give us 2. Again here for this 0 minus of minus 9, 0 minus of minus 9, that is plus 9, so finally it is minus 9. Again for this element we have 0 minus 6, 0 minus 6, that will give me minus 6. Here for this element I'll delete this row and this column, so what we get is this row and this column is deleted, 1 2 to minus 4 plus 4. Minus 1 into 4 is minus 4, minus of minus, so this will give us plus 4, minus 4 plus 4 is 0, so this is 0. Here A22, for this element we will eliminate this row and this column, this row and this row and this column is known, so 1 4s are 4 minus 6, 4 minus 6, 4 minus 6, obviously it is minus 2. Now for this A23, this I will delete this row and this column, so 1 into minus 2, minus 2 plus 3, minus 2 plus 3, minus 2 plus 3, and this negative sign will give me minus 1. Again for this 3 minus 4, 3 minus 4, that is minus 1 multiplied by plus 1 is minus 1. Again here A32, if I talk about this, we will delete this row and this column, so we are here with minus 3 minus 0. So in a bracket minus 3 minus 0, that will give us plus 3. Finally for this element, eliminate this row and this column, so 2 minus 0, 2 minus 0, so this will give us 2. So in 3 lines we can do it. Cofactor of this element, first, second, third, then again first, second, third. Now cofactor matrix, adjoint A. Now adjoint A is equal to transpose of the cofactor matrix, that is transpose of cofactor. We'll write the cofactor in the same order, A11, 12, 13, and then we'll take in the next step we'll take the transpose. So 2 minus 9 minus 6. 2 minus 9 minus 6. 0 minus 2 minus 1. 0 minus 2 minus 1. Minus 1 3 2. Minus 1 3 2. Now on taking transpose, what we get is the first row now become the first column. 2 minus 9 minus 6. The second row becomes the second column. 0 minus 2 minus 1. The third row now becomes minus 1 3 2. This is adjoint A. Hence the A inverse is equal to 1 upon determinant A times of adjoint A. Determinant A is equal to minus 1 actually. Determinant A is equal to minus 1 here. Minus 1 times of this 2 0 minus 1 minus 9 minus 2 3 minus 6 minus 1 2. Now we'll divide each and every term by minus 1, that is we'll change the sign, and the final answer is minus 2 0 plus 1, then plus 9 plus 2 minus 3 6 plus 1 minus 2. This is A inverse. So to find A inverse, what we do? First of all, we need to check whether it is invertible or not, whether the inverse exists or not. So first of all, we find the value of determinant A, that must be non-zero, and here we will write this line, since determinant A is not equal to 0, so A is invertible, or so A inverse exists. So A inverse exists. Now we will proceed to find the A inverse. We need adjoint of A. Adjoint A, what is adjoint A? The transpose of cofactor matrix. Adjoint A is the transpose of cofactor matrix. So now what we do is we find all the cofactors of all the elements. First row I have written in one line. For the elements of second row I have written the cofactor in the second row. Right? Suppose I need to find the cofactor of any of these. Suppose I have 3 2. 3 2 is this third row, second column. For this I write with sign positive or negative. 3 plus 2 is 5 minus 1 raised to 5 is negative. Now 3 2, I will delete this row and this column, so this will give minus 3 minus 0. So minus 3 minus 0, this is minus 3, minus into minus is plus 3. So in a single step you can find the cofactors. Will not write here the determinants and not will use so much of lines. You can do like this, the cofactor of this minus 1 raised to, first of all we can find minor, then we multiply it by minus 1 raised to I plus j. We will not proceed like that, because we are to find the inverse of a matrix, and this inverse of a matrix will further be used to solve the equations, the system of linear equations. So mind it how to do it. Just find the cofactors and just get the transpose of the cofactor matrix. You will get the adjoint A, and as soon as you divide the adjoint A by determinant of A, you get the inverse of a matrix. Well, in next sessions we will talk about inverse of a matrix using matrix equations, and the most important thing, the last but not the least topic, which is solution of linear system of linear equations. Solution of system of linear equation. 2 or 3 simultaneous equations are given, and we are to find the solution of that system of linear equation. Thank you.